Well, hello friends, welcome back to the program. Today we are going to take a look at application startup time on Serenity because I kind of feel like it's gotten a bit slower, and ever since we introduced shared libraries and dynamic linking, we've had kind of a regression in startup time, but it's a bit hard to put my finger on it. But it's starting to feel like things start a bit slower. So today we're going to investigate that and just basically follow wherever that takes us and see what kind of problems we have, what kind of optimizations we can do, and so on. So we'll be starting by tweaking the runner script so that we run without KVM. So normally I run with KVM enabled in the Linux host because that makes everything much faster. But if we run without KVM, then we can sort of flush out performance problems because now we're running QEMU in full system emulation mode instead. So now if we try to start text editor, we can see here that it takes quite a bit of time. So let's, I guess, get a profile of startup here. So we'll just start it up and then stop there, and then we will open it up in our profiler. So what are we looking at? I guess that the first part here is going to be the dynamic linking. So let's look at that. Or yeah, that's dynamic linking. And then here we have, this is sort of libgui startup. And then we have a big window of time here where nothing happens. It's a little suspicious. Almost a whole second of nothing. No idea what the system was doing then, but let's start with looking at the dynamic loader. Also, here's an interesting display problem in the profiler that this looks like a wrapped around integer. Anyway, ignoring that, we can see that during startup, if we switch to a percentage view, then we have a lot of time spent in calculate GNU hash for ELF dynamic objects, and we also have a bunch of time in strlen. So strlen is called by various functions on ELF dynamic object, and the GNU hash is called by lookup symbol. Okay, so I bet we can do less of both of these because it sounds really silly, right? Like the fact that hashing strings and strlen are almost 30% of what we do in the dynamic linker. That's just crazy. So let's see what we can do about those, and then we have a whole bunch of other things here going on, but I think a good strategy in a situation like this is to first try to chop these down and then see sort of what remains after. See which one sort of bubbles up to the top. So let's go and look at, I guess, calculate GNU hash is the biggest one. So calculate GNU hash. Oh, let me switch here to the dynamic. No, wait, that's not what I wanted. Loader.so. I don't know. Sometimes it takes a moment before CLion sort of reacts after I switch which target I'm working on, but I don't hold it against them. So let's see. So this is calculate GNU hash. This is extremely innocent looking hash function. So the ELF spec, or the executable and linkable format, has two different hash functions. There's the system5 ELF hash, which is the original spec hash, and then there's also a GNU extension hash, which we use in all of our executables and libraries because it is a more efficient hashing function. So this is the one we're looking at here. And yeah, right here is the elf hash, as we call it. This is really the system 5 elf hash algorithm. So this is where we are spending most of our time. That's obviously a bit silly. So it's called by lookup GNU symbol. Actually, let's try to use the features here. Okay, so lookup GNU symbol calls it here. Hash1 is calculate GNU hash, sure. And who calls you? You are a function pointer. So dynamic object lookup symbol. This guy right here calls presumably the function pointer. Yeah, okay. So it's really unfortunate that we have to hash that, but I bet you that we're probably hashing the same string many times, and I bet you that we can make a cache somewhere. Like, let's see how this is actually used. We just have to go up the call stack. So this is called by let's see, various places here in initialize libc and in lookup global symbol. Okay, so init libc, this is only called once, just before we start the regular program, but lookup global symbol is going to be called multiple times. And this is essentially when you have a program that links against a bunch of libraries, and then the libraries, they all have symbols from each other that are unresolved, right? So then the dynamic linker has to resolve all those symbols, and then here is where that happens. So say that you want to resolve the symbol malloc, right? Because libjs uses malloc. So then we come in here, the symbol contains malloc, and then we have to iterate our global list of dynamic objects that we are linking against, and then for each library, each global dynamic object, we do a lookup. So this is probably where we can think about the cache. So here we're going to do a lookup in every library. So in a program like I mean, let's even the text editor like that we were just looking at. Let me start one up, and then we can do a pmap on it. So we can see here that it has a whole bunch of, oh, that's so laggy, a whole bunch of dynamic libraries, right? So we have to look in each one of these. So what if we just pre-compute the hash, actually, like the GNU hash, compute GNU hash for the symbol. And then we would pass that in here, GNU hash. And I guess we would have to, we can do it this way for now, that we compute both hashes, but because this is still going to be way less work than doing this for every library. So we'll pass in both flavors, sysb hash as well. And then let's move these out to a helper. So not services, libraries, libelf, hashes.h, maybe? Yeah, so we'll take these two, hashes, and namespace elf, and then let's be good boys and bring with us the copyright header as it was, where we're taking them from, because we're not trying to remove these good boys from history. In fact, let's just leave it like that. but we can make them free functions at least. And in fact, why not also make them const expr while we're here, for the heck of it? And then we just need act types for U32. Actually, we need act string view. Also, I don't know why I was using uint32t here, but now we're not. Okay. So that's pretty good. Also, this looks a bit weird. Let's tweak that. Okay, all right. And then for some reason, I wanted to call these compute sysv hash and compute gnu hash. I don't know why I like compute better than calculate here, but I just kind of do. Also, elf hash I think is better than, or sysv hash is better than elf hash because both are elf hashes, but this is the sysv flavor, or sys5 if you will. So where were these used? So we'll just get rid of those, and let's see. So this one is compute sysv hash, and okay, maybe we should do a first commit where we simply move out the hash functions to their own place here. So I think maybe we'll just do that. And leave this alone for the time being. Okay, and then let's just see if things still boot up. Oh, still running here. Okay, so we're still booting up this fine, so we didn't make any big mess. So let's git add, or I'm supposed to be using the cline git interface, so let's practice. Hashes and not you, but all of these changes, yes, yes, yes. Okay, libelf, move elf hash functions to their own file and make const expr. Yes, that's a little bit of an unexciting commit, but I think it's nice to clean things up before we proceed. Did it work? Oh, it failed. Oh, there's a we have this pre-commit thing, and it's showing me some error here, and we have, it's a bit messy because we use like terminal color escape sequences in the pre-commit hook, so it's a bit hard to read, but it's always that like I have to auto format some files, so or actually it's probably pragma 1's missing in here. I bet that's what it is. That seems to have worked. Cool. Okay, so let's see if we can actually make use of these. So just verifying here that I didn't commit something I didn't want. Yeah, because I still don't really trust myself with the GUI commit. Okay, so let's bring in libelf hashes here. Okay, so now we have two hashes, and then we can just pass those into lookup symbol, which has to, of course, take a sysv hash and a GNU hash. And what does this thing actually do? Lookup symbol. So it's just calling through on a function pointer, right? Yeah. So Like, what if we just get rid of that function pointer, and instead we would do this inline here. So like if m hash type is hash type sys5, then return lookup elf. Elfs, yeah, okay, we need to fix these names. Hash, let's say. Sysv hash, new hash, name and hash. Almost. Sysv hash. Also, oh, we don't have the hash type. I guess we'll have to save that. That's fine. Then yoink. And away with the function pointer. And there we go. So hash value is now an input to this function. This is nice. And we also have the GNU symbol. Where's the hash here? Bloom word hash one. What the heck is a bloom word? Oh, it's just it's just a U32. All right, that's fine. So I guess like you know what? Let's just do this. I don't want to mess with this too much, so we'll follow the exact same pattern as the other one. Okay, and then wait, what don't you like? Oh, where did that come from? Oh, it used to be an argument, and then I just removed it, like a Dumbo. Okay, that's fine. So, then everything is good, and lookup symbol, of course, has now changed a little bit, so it takes a GNU hash and a sysv hash. And we'll pass those along. Okay. Let's see if we can build here. Nope, not quite. Dynamic low adder. Maybe I can build in CLine. That would be cool. Okay, that works. Symbol for name. Okay, so here we don't. Oh, this is used by DLSim. Okay, so this is for like the libc dynamic, like linking with a library at runtime API stuff. So I think maybe we don't need to be like super accommodating, and here we can just like, or it would be nice if this thing just worked automatically, I guess. Let's see, compute, we don't have the header. Hashes, compute, GNU hash, name, compute, sysv hash, name. That's fine, I think. And then here when we're initializing libc, then it looks for a couple of different symbols by name. Environ is malloc, exit, and libc init. So I think for this API, let's make a helper that would just follow the old convention. And if you call that one, then we will just compute the hashes on the fly for you. I think that could be okay. Because the important one is like the global symbol lookup loop that we had. That's the one that we want to actually optimize. Because these are just 4 lookups, but the other one is probably thousands and thousands. So auto GNU hash is, return lookup symbol, name, compute GNU hash name, compute sysv hash name. Wait, what's wrong with that? Oh, const. Yeah, okay, that's my bad. It worked. Cool. Let's see if it actually runs. So I'm not really expecting a miracle from this, but I feel like we should be able to knock it down from the top spot at least. What the heck? This is kernel stuff. There's a null reference in the USB code. That's not what we're here to work on, so skipping over that. This looks more like a crash in our department. Did not find symbol. Okay, so we've broken symbol lookup, presumably. All right, dynamic object 458. We failed to find the symbol. Sure, I believe it. Lookup global symbol probably failed. Oh, wait. Wait, why doesn't it work? That's so weird. Okay, well, I feel like I did everything right. Let's investigate. So this is probably one of the first symbols that we look up, actually. So just thinking if I put the arguments in the wrong order somewhere, that would have been stupid. But I guess not. Let's just print out what we are doing. So lookup global symbol, sure. And these look fine, right? Yeah. GNU hash is this, sysv hash is that. Sure. Let's just try it. Okay, so what are you saying? So we're looking up a couple of things and that works, but then we're failing on this one. Lookup symbol. Wait a tick. This is the wrong order here. But does that matter? Sysv, wait, I'm putting sysv hash first sometimes and GNU hash first other times. Yeah, I had a feeling it was something like that. So let's go and fix that type of stuff first. So here sysv hash is first, but I'm passing GNU hash first. It's annoying when when two things are the same type, because then you make this type of mistake. Lookup symbol. Or rather, I should say, it's nice when things have distinct types so that you don't make this type of mistake. And here was the other one that I screwed up. Yeah, okay. That one was probably, that was really dumb. So, oh, it's that USB thing again. Wonder what that is. Seems to be easy to reproduce when you're not using KVM. Okay, so now we should probably remove that debug statement because it was getting extremely verbose about all the global lookups. So by the way, you can see here that there is just a boatload of these lookups, right? So there is value in optimizing those loops. So still slow, obviously, but let's get a profile and see if we're still at 15% or so of the startup time. If we invert and look at that, where's the hash? It's totally gone, actually. That's very interesting. So, I mean, I did inline it and make it const expert, and here now we crashed the profiler, but that's I would say that's a separate issue. So let's just start it up again and try to get a top view here. Man, I need to test without KVM sometimes just to see these performance issues. So I wanted to look at lookup global symbol, right? So we're still spending 35% of our time in global symbol lookup. But yeah, so the GNU hash issue is basically gone. That's awesome. Now we have strlen instead at 12%, and then when you see the kernel doing stuff in profiles, it's usually a bit annoying because the kernel will disable interrupts here and there, so you don't have full visibility into it because we depend on interrupts for profiling samples. So it will go like for lengths of time without being able to be sampled. So and then you end up getting all your samples in this destructor of scoped spin lock, which is I think also where interrupts get re-enabled. I think that's what's happening. But anyway, 11% in the kernel, like that's tolerable, although almost 5% in kmalloc. Creating strings. But it's file system traversal. Yeah. I mean, we can probably splitting paths into path segments. Here we could probably have a vector with some inline capacity here and get rid of these allocations. Where is this? Resolve path without veil. Vector of, wait, there's a vector here somewhere, right? What were we doing? Why don't I see a vector? Oh, it's probably auto. I'm calling it split view. Split view. Okay, yeah, so we're splitting a path into parts, splitting it around slash character, and split view returns a vector of string view. And the heap allocations in this vector, whenever we split path, you can see that those heap allocations in the kernel are over 1% of startup time here. So that's pretty substantial. So there are some options for that, like for example, you could specialize this whole thing and make a custom splitting thing here, or we could have a templatized splitting function that allows you to provide a template type for the vector. I mean, there are a whole bunch of things we could do, but we could also pre-allocate storage. Anyway, I think we're not going to sweat the 1% right now, so we'll leave that one on the table. Funny thing about leaving stuff like this on the table is, as you progress through the other stuff and remove other bottlenecks, then these the remaining bottlenecks will grow, right, percentage-wise, because they are now relatively larger, and that's kind of fun. So maybe this 1% will become 2% if we get rid of something else stupid. Anyway, so Sterlen, what's going on with that? So we have symbol name. Sterlen, do relocation. So whenever we get the name of a symbol from a dynamic object, then we have to fetch the name from the symbol from the string table in the elf, and then we do a strlen, I guess, because it's string view. So we'll implicitly call strlen to figure out how long it is. That's kind of annoying. So let's look at do relocation. So this is sort of the workhorse function of the dynamic loader that performs one single relocation, and we do a lot of relocations. So who's calling name here? Here's the first name. Although it's debug line if. Oh, wait. Oh, I wonder. So that's interesting. So debug line if is basically what this means here is that like this, we will only print this debug statement or run this debug thing if this is true, if this is defined to true, and it's not true by default. But will we still compute the result of this expression here? I think we might, because even if, wait, what was that? Dynamic load debug. Even if this is like 0, this is false at compile time, but we will probably still do that expression. Oh man, okay, so wait, so what if we just do this? So we'll just kick those out like that. Or you know what if we just get rid of all of this debugging thing here anyway, because the linker is, or the dynamic loader is, I would say, sufficiently stable at this point that we don't need all of this bring up debug code. And if somebody actually does need it, then we can go ahead and add it back. But I feel like I can't even turn on this debug flag anyway because it's so spammy. So it's all just sitting here, not being used. So let's just get rid of it. And here's a printf. Let's get rid of that too. Yeah, so let's see how that affects it. I mean, it wasn't the only source of strlens, but it was the biggest one. So let's see if that helps. Of course, now we're doing a cold one, like we don't have the binaries in cache, but even so. Invert. Strlen, right here. So do relocation is actually gone from here. That's cool. So yeah, so okay, so I guess those debug line if will still evaluate all the expressions that you're passing into it, right? So you got to be careful with anything that has side effects or performance implications if you're using debug line if. I guess I should have thought of that before, but I just kind of slipped my mind. Foo debug, right? Like, so then you're doing something, and then like foo.expensive thing to check. So even if this is false, we will still always do the expensive thing to check. So solution, I think, is to simply do this instead, in case you have something expensive. It's not super intuitive, but I don't know that there's another solution for that right now. I don't know. Maybe somebody who's watching has some ideas about that. I know Ali knows a lot about this stuff. Anyway, moving on. So I think we're just gonna wholesale nuke all of the debug line if in this function, or in this whole file, because, you know, whatever. Let's just get rid of them. And then we can apologize later. What do we have here? Dump. Never needed it. Okay. So that's dynamic loader CPP. Let's go ahead and commit all of those changes then. Just patching out all the debug code seems to have a strong performance benefit, so let's do it. Libelf. Oh, now I'm committing in the terminal. Oh, whatever. Remove an ungodly amount of dynamic load debug logging. Debug line if foo debug. We have to be careful with foo, where foo is something expensive, since it might get evaluated even if not foo debug. This logging mode was unusable anyway, since it spams way too much, and if we need to add some debug, the dynamic loader is in a good place, pretty good place now anyway, so I think it's okay for us to drop some of the bring up debugging logging. Yeah, okay. And then what do we have? We have the using the hashes and caching the hashes in the global lookup function. Yeah, I think we can commit that. Yep. And yep. Elf. Don't recompute elf hashes or the same elf hashes over and over. When performing a global symbol lookup, we were recomputing the elf symbol hashes once for every library searched, every dynamic object searched. That the result was that, or no, the hash function used was at the very top of profile, when top of a profile of program startup. Yeah. 15%. This patch eliminates eliminates and removed that stack from the profile. With this change, that the hash function is no longer visible among the top stacks in the profile. Oh, I made a spelling mistake. Has function. Okay. So what's next? I guess we should have looked at who else was calling strlen, because I got carried away with removing those debug statements, but strlen was still popular, so let's pursue that a little bit more. So I guess we'll do it. We do a cold run first, so we get everything into cache, and then we will profile text editor starting up, and oops. Okay, so what do we have here? So symbol lookup is still up top. strlen is 7.7% now. So that's kind of cool. And what's going on in the kernel anyway? So kmalloc string create vector. So that, see that, wait, what kind of vector is that? It's some other vector. Oh, right, because in the last time we were looking at a cold profile. So I guess path lookups is probably faster now that things are warm. Anyway, strlen is still called by hash section. Hash section? Wait, why is hash section calling strlen? That makes no sense. Wait, is this implied strlen here? Create a section with section name. Section is what? It's a string view. Oh no. Oh, we're strlening these to create a string view, even though they are compile time. Even though you can see the size of compile time, that's so stupid. Yeah, okay, so we shouldn't be doing that. And I don't want to mess with string view right now, because then there will be like 5 billion thousand files to recompile. So let's just do a little hackamundo here. So we'll do something like this. And by the way, here's a feature I love in CLion. If I select some text like this, then down here it says how many characters I've selected. I never realized how much I would want a feature like that. It's so neat. Because now I know it's 7, so I can easily do this, which is hackish, but we are just going to plow forward here. That's 11. Okay. So then we can pass that. That's almost 3% of the profile. So let's see if that actually disappears it. If so, that's a really cheap hack. And then we should definitely go and try to make string view able to recognize that something is compile time string literal, and like just do this automatically. That's I would leave that as an exercise for later. But let's warm it up. Okay, and then get a profile. And it's funny how the profile always looks a little visually different, but strlen. is now 8.62% of this profile. So, well, at least the hash section is not calling strlen anymore, so that's good. Now it's only symbol table string, and it's only symbol name called by lookup new symbol. So that's the one who dominates. Maybe we can get rid of some of those too. Maybe it's something stupid going on. Let's take a look. First though, let's commit here. So these are the things to commit, sure, and then libelf. Don't avoid calling. Avoid implicitly calling strlen in dynamic object hash section. Yeah, I mean, so okay, so the long-term fix here is to make string view recognize compile time string literals and do the right thing automatically. I'm not gonna make excuses for myself. I'm just gonna say that that is the correct long-term fix. Okay, yeah, and this change we don't want to commit, obviously, because it's just hacking the run script to turn off KVM. So let's go and look at, what was it, lookup GNU symbol. Oh, by the way, like this lookup elf symbol name is kind of bothering me, so let's change that to lookup sys5 symbol. And, oh, I don't know what's going on with this. This is here for completeness. Okay, well, fine, whatever. Just checking that we have renamed everything correctly. Yeah. Rename lookup elf symbol, lookup sysv symbol. Yeah, we have two kinds of lookup, sysv and GNU style. Both are elf lookups. Yeah. Okay. So we wanted to look at the GNU symbol, see what it's doing with name. So let's just search for name. Okay, so we have a debug line if here, right here actually, doing the stupid thing again. So we can probably nuke that. But then we also have here symbol name. Let's see, so what is this doing? It's iterating over a hash table chain. Okay, so name is the input, right? Yep. So, and then we have symbol name here. Oh, interesting. So we can get rid of one of those calls to name, but the other one remains. Let's see how much it does to just do one of them. So the problem is, of course, that name has to return a string view, and elf names are, they're C strings inside of the binary format. So like in the elf tables, they just point you at an address, and then you have to read an alternated string from there, but you don't know how long it's going to be. So what we do in libelf is that we just read the string, we do a strlen on the string in the elf binary, and then we create a string view once we know the length. That's happening here because we're passing a C string implicit, and then it turns into an implicit strlen in the string view constructor. But this is kind of annoying because what if it's a mismatch and you could reject it much earlier, right? So we end up like doing a strlen on potentially like pretty long names, right? Even though even the first character would be a mismatch. So we could fail a lot faster, I think. But let's see how much this actually mattered that we got rid of one of them. Just out of curiosity. Oops. Okay, strlen still up top. Yeah, it's still here. Okay, well, how about we do something like this? Raw symbol tables. So we'll offer an optimized unsafe version here. Yeah, and then, you know, use at your own risk. But if we do that, then we can use raw name here, and string view actually has a fast path for that, so that should be better. So now we don't have to do a strlen, but instead it will just like go character by character and it won't traverse the whole string. It will just go character by character, and immediately when there's a mismatch, it will just reject that symbol, potentially avoiding a bunch of work. So let's see if it actually helps us. Part of me thinks I should automate these steps, but it's kind of it gives me a chance to think a little bit while I'm doing the mechanical steps. So lookup GNU symbol is up here, but ooh, where is strlen? Where did our friend strlen go? Obviously strlen is gone because the thing that was calling them the most is no longer doing that. Where is strlen? Down here, look at him. All sad, less than 1%. That's very cool. So now instead, I guess this function eats the cost of it, but it should be less work regardless. And what's malloc doing? If we wow, profiler is crashy, man. Okay, well, I'm happy with that change anyway. So let's go ahead and commit that. Getting rid of the dynamic load debug thing, and yeah, exactly. So like elf avoid doing strlen on everything while iterating GNU hash table, GNU hash. It's a lot faster to iterate the GNU hash tables if we don't have to compute the length of every symbol name before rejecting it anyway while comparing the first character. Yeah. Yes. So I think that's a fair change. And what else do we want to do? Something else I've been thinking about is, I mean, actually, maybe we should have started with this, but I've been thinking about, like, why don't we try to build the system with like optimizations? Because currently we're building with OS right here. This is our like default build flags, and why don't we like build with O2 or O3, right? So let's just try to go. Let's just try to go O2. Okay, so we have some problem in die CPP. Wait, 82. Wait, am I in the right place? Die CPP 82. Offset may be used uninitialized. Oh, because we don't recover from errors on the stream? So like, has any error? If so, is Xert not reached? Something like that. You know what, let's just do this. It's a little bit lazy maybe, but at least it makes us not continue if the stream had a reading problem, and then we don't use uninitialized data in these functions. It's kind of interesting that when you turn on optimizations, then the compiler finds more problems. I like that. That's a very interesting side effect. So was that everything? That looks like maybe that was everything. Cool. So what if we just run that? Oh wait, I have to build an image. It doesn't boot. Also, what are these? I think these are from QEMU. I installed a new version of QEMU earlier today, and probably these are error messages from QEMU, but we've been getting them the whole time in this video. I just wasn't really mentioning it. So, but what the frick? So let's see if we can enable some like debug info in QEMU here and see what's happening. Okay, so we're getting CPU reset for some reason. Let's look at where we are. EIP is, that looks like a kernel address. So we have a reset at this address. Adder to line, kernel, studlib 281. Sterlen. All right. So, oops, wait, what was the name of that address again? This, right. So we're in Sterlen and we're failing. So trying to compare byte at address EDX, sure. So what was EDX when we crashed? Crash here, EDX is here. So I think this reminds me of something that somebody was trying to enable more kubesan options a while back. Like after I did the initial kubesan bring up, then people have been adding more kubesan things, but there were some kubesan options. Undefined sanitizer, where is it? Here, right. So we're enabling all of these different undefined behavior sanitizer flags because they work, but then we have these that cause triple faults. And I feel like they were in strlen. So maybe we're hitting the same issue here. Okay, well, we are gonna let's just approach this the slow and ugly way. So we will print out a character on the console to see see where we are. So the console is at hex E9, so we'll just say H for hello. And I guess we can actually, you know, let's just halt the CPU here so that we see that. So we see that we get there. H is for hello. Okay, so we get to here, sure. So now we're in init. Okay, so let's move that below here and print an E. E is for hello. Okay, so we're already screwing up in setup serial debug. Something goes wrong in here because of what? So what this will do is that it will find the kernel command line that was passed to us by the bootloader, and then see if the command line contains the string serial debug. Okay, so let's just print an X here and a Y here, and now we're getting real scientific here, a Z and a Q. And we'll see how many of those we can get. Okay, so we're looping, and oh man, that's so wordy. There's a triple fault here. HXY. So here, here, and then here, and then here is where we die. So string view, again, we'll call strlen on this, on the command line. So presumably we are probably page faulting when trying to read the kernel command line. So where is it? HXY. I guess the EDX tells us where it is because that's where we're trying to read from. So we think it's here. Okay. So wait. We only mapped the bottom 8 megabytes in our boot code. So this is above the 8 megabyte mark. So maybe it's just that when we build with O2, then the kernel grows so much that it sort of pushes the command line over the 8 megabyte mark in memory, and then we don't map that, and that's why we're page faulting. So that that would explain why the kubsan thing broke as well, right? Because maybe that just bloated the kernel so much with the instrumentation code that the command line was sort of pushed past the end of what we were mapping. Because, let's see, so these are the page table mappings for physical memory. So we make these pseudo identity mappings. So the bottom 8 megabytes of physical memory is mapped at address 3 gigabyte, starting at the virtual address 3 gig, we map the initial bottom 8 megabytes of the physical address space. So these are the mappings that we're setting up here. But it's only the first 8 megabytes. So from 3072 up all the way up to 3080. And I guess I assumed that the bootloader would always put the command line at a low memory location, because the bootloader information struct is always at a low address. But I guess the command line that it points to could be anywhere. So wait, let's hold on. Multi-boot spec. Where's the command line? Right here. Okay, so this is the format of the information struct thingy. So the command line is a pointer that is 16 bytes into the info struct. And then this jackass is pointing like above the 8 meg mark, which we haven't mapped. So how large is our kernel now anyway? File size, mem size. It's a little bit of a chunky boy. But it's not 8 megs, so it's getting bigger though. Anyway, I think what we can do here is just to avoid this problem, what if we just copy out the command line into a separate buffer, and then we don't have to follow some pointer that we don't know where it goes anyway. Because like when we enter into this boot code here, at this point, like everything is identity mapped. So every virtual address just maps to the exact same physical address. And it's just then we start to get fancy with our page tables and like move the kernel above the 3 gig mark and stuff like that. But when we enter here, everything is identity mapped. So we could just take the kernel command line and put it into a. We can just make like a little buffer here, actually, because why not? So we just put it next to the stack, like global kernel command line, right? Skip 1 page. I think that's probably okay. And then, what do we want to do? We want to copy everything, or we want to copy like 4 kilobytes from this pointer. Who's pointing to it? Machine state. So when we were called, we have these registers. This magic value, and then EBX points to the multi-boot info structure. So EBX here will already point to the structure, and we just need to go 16 bytes into it to get the address of the command line. So if we just need to move this into the source register, and then I don't know, I'm just gonna write this in kind of crappy assembly because who cares? And then we will wait. How do you do this again? I'm not super strong with AT&T syntax, so this is a little bit slow. So we're taking whatever is at this memory location and loading it into the source register itself. Sure. And then we want to do a copy. So we can do 4 bytes at a time, 32-bit copy. So we'll move this into ECX, and then the destination is going to be the kernel command line minus 3 gig. So we have to do this because of the, like when we build the kernel and link it, then the kernel puts everything over the 3 gig mark because that's where it will eventually run. So all of the symbols that we talk about here, even though they're not actually mapped there yet, we have to subtract and stuff because because we tell the assembler that, no, don't worry, these are over the 3 gig mark, even though that's not true yet. So that's why you see this happening here, doing like manual relocation at compile time. So we'll move this into the destination, and then we will simply rep mobsl. Okay, so copy the kernel command line to a buffer in a known location. This avoids having to deal with it. Otherwise, it might. We don't know where the bootloader might have put the kernel command line. It might be at an inconvenient location that we're not about to map. So let's just copy it to a convenient location while we have the whole memory space identity mapped anyway. Yes, so that's pretty neat. And then in the init code, we can just, instead of doing this, where we try to, this is essentially doing this hack to add or remove the 3 gig mark from these addresses. So we don't need to do that anymore because we can just declare it as an extern. Something like extern C char kernel command line 4096. Boom. So then kernel command line, can we just do that? Yep. That would be so sweet if this just works. And then this also becomes a lot easier. Wow. Kernel. Okay. Let's see if that works. Wouldn't that be nice? Undefined reference to kernel command line. Well, that didn't last very long. Wait. Did I do something wrong with that? Kernel command line. Oh, wait. I was inconsistent. Nice. There we go. Cool. Dude. We're actually running with O2, I guess. Oh, dude, that's so nice. So that was the only thing standing in our way this whole time. Let's see if we actually capture the command line, though. Yeah, it's here. This is the kernel command line. Fine. So let's get a profile of text editor. Yeah, definitely approached this in a very strange order. Like, did the optimization work first and then turned on the optimization flags. Should probably have done this the other way around, but that's what happened. So no big deal. So now lookup GNU symbol, totally dominating here with almost 18% of time. Sterlen rearing his ugly head. But it's not so bad. Lookup symbol. Right, so if a symbol is undefined or if it's a weak symbol, then we have to do a lookup by name. That makes sense. it makes sense that we wouldn't have the name by the time we're here. Although, who calls this? Who calls it? It's a lambda for do main relocations. Do main relocks calls do single relocation. Wait, what? Lookup symbol. Oh, I guess this thing is doing it. Okay, this is a little bit confusing. Yeah, right. Because I'm so used to not building with O2, but like once you start building with optimizations, then some stack frames disappear here and there because compiler likes to optimize things. So the profile is a bit less trustworthy because of that, which is annoying. Or at least like frames go missing. But still, this is it's interesting. So I wonder how this feels with KVM. Kaboom! Let's just let me just try that. That's not bad. That actually feels very fast. Very cool, actually. Browser is a little bit slower than text editor, obviously, because it does a lot more, but that's still very snappy. Interesting. So, oh, dude, let's do the JavaScript test suite. So it runs, when warm, it runs in like under 700 milliseconds. That's cool. Should have had something to compare against. But this is awesome, dude. Like, I wonder what happens if we build with O3. Or you know what? Let's do something else. Let's commit first, and then we can do the kubesand things, because I bet you that we can maybe even just enable those. So first we have these changes in die CPP to make it compile with O2. So libdebug. Make fix build with -O2. It turns out that libdebug was the only thing that couldn't be built with O2. We were neglecting to deal with stream read errors. Some stream read errors, sure. And let's do the boot code. So the kernel command line thing, just moving that into a buffer that we control the location of so that it doesn't run away. Copy the kernel command line to a known at boot to a good location, let's say. I'm building the kernel with O2. We somehow ended up with the kernel command line in outside of the lower 8 meg of physical memory. That's since we don't map that area in our initial page table setup, we would page fault when trying to read, or let's say we would triple fault when trying to parse the command line. This patch sidesteps the issue by copying the first for kbf kernel command line to a buffer in a known safe location at boot. Yeah. Yeah, that's okay. I'm okay with that. It's like a little bit of a hack, but it beats dealing with the like changing the page table layout, because I don't want to deal with that right now. Okay, and then why don't we just flip on the O2 build? Like, who's going to stop us? Everywhere. Build with -O2. Let's try going faster instead of smaller. This. Let's put one of those things. Yes. So let's see. Do we want to try kubsan or O3? Let's do kubsan. So what if we just like just enable all of these flags, right? Then what happens? Okay, well that clearly didn't do everything right. Oh, wait. Let's try it, and it works. Okay. And no kubsan complaints? Nope. Let's just run some code. Go to the internet. Oh, no kubsan. No kubsan complaints. That's really cool. So I bet you that we've solved that entire problem. And we can stop specifying individual options like this and just turn on all of them. So we can just do this. We could probably even do that. And just turn on fsanitize undefined wholesale. That would be really cool. And then Brian started working on ksan as well, kernel address sanitizer. But that's, as it says here, still a work in progress. But that's going to be really cool when we get that working as well. Looking forward to that. But yeah, like if we can run the complete undefined behavior sanitizer always on in the kernel, I think that's super positive. That's like, I really like that. Because I'm a big fan of just catching errors immediately, like failing spectacularly so that you can actually fix stuff instead of trying to paper over your problems. And kubsan is great for that. Okay, so this doesn't quite work. All right. I wonder why. Tempted to do a clean build now because I kind of don't trust this. Maybe I was getting overeager trying to build everything, all the options. Maybe there's some other option that I don't know about. Yeah, because now we're boot looping again. All right. Why are we boot looping? EIP. So we're crashing here. I mean, maybe it's an oopsan crash. So let's see, adder to line. Don't know where that is. Sure. That is in init. It's in the code leading up to init. Wait, what? What is this address? Oh, wait. Did we actually bloat up the kernel so much now that it doesn't fit in the bottom 8 meg anymore? But wait, then why was it working when we did it this way? Why is that working? Like if we enable all of those options, but like not fsanitize undefined, I don't know what the difference is. Okay, so I'm a little bit confused by this. I thought that like this was everything and fsanitize undefined, but maybe it's not. Maybe there's more to it. Seems like there's probably more to it then. Okay, well I'm not gonna get into all of that. So we'll just enable those since they work now, and then I guess we'll have to deal with more of them at some other time. But I do think that there seems to be an issue that like the kernel is starting to get so big that space is becoming an issue. Like we've been fitting in the bottom 8 megs comfortably with building with OS, but seems like maybe we need to expand a little bit. But I'm not going to do that now. I need to wrap things up here pretty soon. So enable the three missing koopsan options. With the kernel command line issue fixed, we can now enable these koopsan options without getting triple faults on startup. And then, what were they actually? Alignment, null, and pointer overflow. And is that how I formatted my things last time? Yes, it was. Cool. Well, that's cool. Okay, so I guess if we build O3, I can already guess that we're not gonna have enough space in the frickin' page tables. But let's just try it anyway for the heck of it. So we'll go O3. Oh, and actually maybe we can just downsize to O2 in the kernel. So kernel only goes O2. What if we just did that? Also, there's some CMake thing that we're not using here for setting compile options. There we go. Yeah, this will take a hot minute. Still, I'm very interested in seeing how this will go. Oh, go faster, bro. Was there something else that I wanted to do? I feel like I probably mentioned a bunch of things I wanted to do next, but they fell out of my head. So let's try running this. And we die in storage management. That's not really what I was expecting. Invalid signature in the master boot record. Wonder if we actually built the kernel with O2. I'm gonna do some hacks here to ensure that we get O2, just to test it out. I never remember if O2 goes first or last. Like, if you want it to be like, this is the one that you should use, should it go before the other options or after? Like, which one does it which one does it honor? I could probably look that up somewhere, but it's not the end of the world. We will hack it and see if we can boot it. I would just like to see it boot. Okay, so there's some trouble with O3. I'm not going to look into that today. So let's just get rid of that, and I mean that, and that, and that. And we should be in a good place. So we have done a little bit of work on dynamic loader performance. So we got rid of all that redundant hashing that we were doing, hashing over and over the same things. Now we only hash every symbol that we do a global lookup on once, instead of for every library that we search. That's good. We got rid of a whole bunch of implicit strlen because of string view. We got rid of a whole bunch of debug code that had side effects, and we enabled kubesan options. We got everything building with O2. That's really cool. The command line is now at a location that's safe, independent of page table layout, so that's really good. Yeah, I guess those were our changes. So a whole bunch of little things, but I'm very happy with them. And I think we're probably going to be done here for today. I just want to see. It would be nice to get this to boot really fast again, because it used to boot really fast a long time ago without KVM. But of course, we do so much more now. When you boot the system, like, we have to dynamically link everything, and we have all these different programs spawning at startup. So it's a challenge, but I think it's worth like sitting down and figuring out what's actually taking the time and trying to improve it. And yeah, it's not instant, but it is significantly faster than what we started. So take one last look at the profile. That's not what I meant to do. Why are you so crashy? This silly app. Profile viewer need to be worked on a little bit. Yeah, so like, I bet that there's more stuff here that we can do. What's this? Elf image parse. What's even going on in there? Let's flip this thing around, actually. See what's taking time from the top view. So we have linker main, load stage 2, sure. Commit elf, and then like constructing all the widgets and stuff. And oh, we're good. Almost 20% of syscall. That's interesting. mmap is heavy. What are we doing in mmap? Allocating space. Sure, makes sense. That's what you do in mmap. Okay. Yeah, I mean, 20% is syscalls. There's definitely like still huge amounts of improvements that we can and should make here, but I'm not going to do any more today. I'll leave it for the future. So yeah, this will be the end of today's video. I think we did some good stuff. So I would like to thank you very much for watching, for hanging out, and I hope that you saw something interesting. I think all of these kind of systems are they're very fun to mess with and like to see how they all interact, like the boot sequence and the kernel and the dynamic loader and the compiler and everything. And it's a fun little system to mess with. And it's really, I really enjoy using the profile-driven workflow like this, just figuring out what's going on and then trying to iron out how to get rid of it. Anyway, this was fun. So thank you very much for hanging out, and I will see you next time, I guess. Bye.